Hello everyone and welcome to this lecture on troubleshooting clusters. Checking the cluster nodes. The initial step in debugging your cluster is to confirm whether all nodes have been correctly registered. This can be done by running the kubectl get nodes command. Ensure that all the nodes you expect to see are present and they are all in the ready state. To obtain more detailed information about the overall health of your cluster, execute the command kubectl cluster info dump. Debugging a down or an unreachable node. When debugging, we might need to assess the status of a node due to observed strange behaviors of a pod or inability to schedule a pod onto the node. We use commands such as kubectl describe node and kubectl get node -o-yaml to fetch comprehensive information about nodes. This information is essential for understanding why a node might be down. If a node is in not ready status, it indicates that it might be disconnected from the network or its kubelet has stopped and won't restart. Pods running on such a node will be evicted after 5 minutes of not ready status. Debugging a node using kubectl debug node command. So you can use kubectl debug node / followed by the node name. It can be worker1, worker2, whatever node name you have. So you have to do kubectl get nodes first. Then you can do -it. This is for interactive and TTY. Then you can interactive and TTY. So you will get a shell onto this particular node, and then you run a ephemeral container, for example Ubuntu in this example, and then you will have access to the direct to the node through this particular command. And this command is helpful in scenarios where you cannot access your node by using the SSH connection. So you can just log in to the kubectl client and use this to get into. So you can replace this with worker1, worker2, whichever node you want to debug. So when you log in through debug node command, these are the log files which will be available. So you have host var log kubelet.log. So this is /host. That's why this is the node worker node, and logs from kubelet responsible for running containers on the node. Then you have var log kubeproxy, which is logs from kubeproxy, which is responsible for directing traffic to service endpoints. Then you have var log container dlog, logs from container d process running on the node. Var log syslog shows general messages and information regarding the system, and then var log kernel log, which shows kernel logs. So the debugging pod can access the root file system of the node mounted on /host in the pod. If you run your kubelet in a file system namespace, the debugging pod sees the root for that namespace, not for the entire node. For a typical Linux node, you can look at the following paths to find relevant logs. So these are the following paths. The debug command helps to gather information and troubleshoot issues, and commands that you might use include, for example, IP, ifconfig, netcat, ncping, ps for process, and so on. You can also install other tools such as mtr, tcpdump, and curl from the respective package manager. Examining logs for in-depth investigation. When a detailed investigation is necessary, logging into the relevant machines and accessing their log files provides valuable insights into potential issues. Logs on the control plane nodes are crucial for understanding the functioning of the API server, which serves the API, scheduler, which makes scheduling decisions, and controller manager, which runs most Kubernetes built-in controllers. Logs on the worker nodes provide information about the kubelet, responsible for running containers on the node, and the kubeproxy, responsible for directing traffic to service endpoints. So control plane nodes, these are the important log file location. This is, you can say, control plane or master node. So we have var log kube API server, var log kube scheduler, var log kube controller manager, and these component API server, scheduler, and controller manager. This is for serving the API. Next one, kube scheduler, responsible for making scheduling decisions, and third one, controller manager, runs most Kubernetes built-in controllers except for scheduling, this one. Then on the worker nodes, you have var log kubelet.log, which is for the kubelet component and responsible for running containers on the node. And then you have var log kubeproxy.log, which is for kubeproxy component, responsible for directing traffic to service endpoints. Okay, potential cluster failure modes. A variety of issues can cause cluster failures, including virtual machine shutdown, network partition within the cluster or between the cluster and users, crashes in the Kubernetes software, data loss or unavailability of persistent storage, and operator errors. When the API server virtual machine VM shuts down or the API server crashes, it becomes impossible to stop, update or start new pods, services and replication controllers. However, existing pods and services should continue to work normally unless they depend on the Kubernetes API. If the API server's backing storage is lost, the Kube API server component fails to start successfully and become unhealthy, and the kubelets cannot reach it. However, they will continue to run the same pods and provide the same service proxying. Manual recovery or recreation of the API server state is necessary before the API server is restarted. Mitigation strategies for cluster failures. There are several strategies to mitigate the impact of cluster failures. These include setting up redundant systems and data backups, implementing load balancing, testing for network partitions, and continuously monitoring cluster performance. Managed Kubernetes services such as GKE, Google Kubernetes Engine, EKS, Elastic Kubernetes Service or Azure Kubernetes AKS Kubernetes Service can help reduce the risk of some types of failures such as API server crashes or data loss by providing out-of-box high availability and automatic updates. Lastly, understanding your application's requirements and usage patterns will enable you to develop suitable recovery strategies. Different applications may have different tolerances for downtime, data loss, or inconsistent state. Disaster recovery planning. A sound disaster recovery plan starts with identifying the critical assets such as essential Kubernetes components and application-specific resources. This is followed by determining recovery objectives which outline the desired outcome of the recovery process. The plan is then developed, which involves steps like creating frequent backups of cluster data and ensuring they are stored safely. Implementing this plan becomes a part of the routine operations. Regular disaster recovery drills are critical. They ensure that the recovery plan works as expected and the team is well acquainted with the steps they need to follow in the event of a real disaster. So, summary and final thoughts. Regular monitoring of the health and performance of a Kubernetes cluster as well as timely debugging of any issues that arise are integral to maintaining the cluster stability. Understanding the potential failure modes of a Kubernetes cluster allows us to design and implement effective mitigation strategies, reducing the impact of any issues that may occur. Lastly, a well-planned and regularly tested disaster recovery plan is paramount to ensure business continuity in the face of severe cluster failures. And that's all. Thanks for watching.